So we have been talking about density of states, local density of states, and I gave you some derivations, wrote something up, hopefully very carefully, and that it could be understood. And there's something I like to go over with this lecture notes, again with you, density of states, local density of states, kind of thing. Just a brief overview. We say that when you have a box, and then if you use periodic boundary conditions on the walls of the box, you give rise to discretized eigenvalues. You give rise to k, which is discretized. L pi 2L pi over A plus y hat 2m pi over B plus B hat 2p pi over P. Okay, so this is kx, this is ky, this is kz, and they're all discretized. And in two dimensions, it's quite easy to draw them. They will correspond to points in the kx. This is kx and this is ky. It will correspond to points in the kx ky plane in 2D. And then we count them by observing the fact that each of these will occupy an area which is like 2 pi over A times 2 pi over B in 2D. And then if you have an annulus of region, if you have an annulus region, this is an annulus, then you can count the number of modes inside the annulus region very easily. That annulus in two dimensions is given by 2 pi k delta k. And then the size of each mode is given by this over here is 2 pi square over AB, which is the area of each mode. And so this is given by the area. AB is equal to the area divided by 2 pi divided by k delta k. So this is the number of modes we have in this annulus region. In 3D, we say that the formula is very simple, similar, except that this thing becomes like 2 pi over A times 2 pi over B times 2 pi over C. That number becomes that number over there, and it becomes 2 pi cubed over B. Okay? So that was the little volume. So if you have a hemispheric shell, or not hemispheric shell, a spherical shell, then that spherical shell has volume of 4 pi k squared delta k, and then if you divide by this volume, that gives you the number of modes you have in a spherical shell in a k space. Okay, and this number turns out to be, let me see, this is 8, this is half pi squared k squared delta k over b, okay? But usually we multiply by 2 because they are actually 2 polarizations per mode. This one maybe not. This one every mode, maybe also still 2 polarization, one horizontal, one vertical. So we usually multiply by 2 because every mode has 2 polarizations. So the number of states between a spherical shell is given by that. And I also say that the density of states is given by this very elegant formula. given by this rather elegant looking formula. Yes?
Why is density of states considered an annulus?
Consider what?
Why do we consider an annulus?
Oh, I'm not counting the density of states here actually. I'm counting the number of states in the annulus region.
Why annulus? Why not
It's
count?
easy to count. I can also, if I know how to count in an annulus, I can integrate this to find the number of states in a circle, for instance. I can also integrate this number over an arbitrary shape, but it's harder to integrate, right? Because this is a circularly symmetric function. It's very easy to integrate on a circle. Okay? This is different from here. And this is a spherically symmetric function. It's very easy to integrate. Right? So this is easy to count in this manner. But if you choose other shapes, you can still possibly integrate it numerically, but not so easy to count.
No, my question is why not a sphere? Why an annulus?
Or once you have an annulus, you can generalize it to a sphere very easily. Right? This is annulus, you can generalize it to a circle by just integrating this. N will be given by a over pi a squared over 2. By integrating, this will be the number of states inside a circle, just by that integration rule. We can do the same thing to find the number of states you have in a sphere, once you know the annulus. But what I'm saying is that if you were to say, look for the number of states you have in the circle with this formula, what would you do? Okay? This is assuming that everything is countably infinite in the K space. So there is a general rule of thumb that sum over K is the same as sum over Kx, Ky, Kz is the same as sum over L and N is the same as sum over delta Kx, delta Ky, delta Kz, and then divide by this number again. But what is delta Kx? Delta Kx is just equal to the discretization of Kx in this manner is 2 pi over A. Delta Ky is 2 pi over B. Delta Kz is 2 pi over C. Okay, so this integral, this summation can be written as that, and then divided by itself again. Dividing it by itself will be divided by this number, which is b over 8 pi cubed. If I multiply this thing out, I define b to be a, b, c, I get this. Okay, so summation over k is the same as doing that. And doing that is the same as doing this. The same as doing that, right? Summation over k is the same as doing that. And this is a trick that physicists often use. I just want to teach this trick to you. So given that you know how to count with discrete modes, you can always convert your discrete modes into an integral. And then if you look at this thing again, you can convert this into 8 pi squared. If everything is spherically symmetric, if you're integrating a spherically symmetric function, like just a function of k, this can be converted into 4 pi k squared delta k, f of k, 0 to infinity. So that can be converted into that integral. Okay? So by the same rule of converting this into an integral, I can convert this into b over 8 pi cubed, 0 to infinity, because epsilon of kn is actually equal to h bar kc. Okay, it's h bar omega, which is a function of k, but then if you convert this into k number, it's just h bar kc. That is E of k. And hence this is the same as integrating this thing, 4 pi k squared. This should be dk, sorry, this should be dk delta E minus h bar kc. And then I have to multiply by 2 because there are 2 modes for every polarization. There are two polarizations for every mode, so I have to multiply by 2. So if I were to count that and convert that into integral, that would be the integral I have to perform. Okay, that is the integral I have to perform. And then this number here is h bar omega naught, which is h bar k naught c. The k naught c is the wave number of free space. So if I were to integrate that, this would be b over 4 pi cubed. And then I put a 4 pi outside. So I get pi squared, 0 to infinity, k squared dk, delta h bar k naught c minus h bar kc. Okay? And how do I integrate the delta function? How do I integrate that? If I were to integrate this, then I would multiply this by h squared c squared, or multiply this by hc, and then divide this by v over pi h cubed c cubed, right? I can multiply this by h squared c squared, multiply by this by h thing. And then say that this integral is actually eta squared the eta delta eta naught minus eta. And eta naught is just h bar k naught c. I can do a change of variable and convert that into that integral over there. And this integral will just give me, if I were to integrate this now, this will just give me eta naught cube squared. Sorry, eta naught squared. So I have b eta naught squared over pi h cubed c cubed. But eta naught is given by this. So this will be equal to b h squared k naught squared c squared pi h cube k naught cube c cube and then k naught cube, right? It's just equal to that, right? So if that is equal to that, I can cancel this, and this will be b k naught cube h bar k naught c. But h bar k naught c is h bar omega is just e. So this will just give me b k naught cube over e.
How did you get the extra k naught cube?
Let me see how I get it. Eta naught is equal to this number over here, right? If I do a change of variable from here to here, to do the change of variable and multiply this by h bar c, multiply this by h bar square c square, and then because they are in total h bar cube c cube, I take it out, and then I can call this eta square, the eta, right? Then this should be eta naught eta, right? And then when I integrate, I should get eta naught squared by the shifting property of the delta function. And then I have this. And then at this stage, I say eta naught is just equal to that, so it's h squared k naught squared c squared. And then the denominator is h cubed c cubed. I put a k naught cube here, put a k naught cube out there. And then now I can cancel these two from leaving me behind with that. And then when I integrate this, I should have this as the number. So if I take this number and multiply by delta E, that should give me the number of states between the annulus region. If I take that number, which I find to be this number here is the result of performing this summation, converting into an integral, and perform a closed form. Okay? So delta E is found to be V K naught cubed over E. And then the number of modes between an annulus region, because this is the definition of the density of states, which is number of states per unit energy. This will give me the energy for,
I think you're missing a pi.
I'm using a pi squared. Yeah, it's a pi here, right? It's a pi squared. It's a pi squared here. Sorry. It's a pi squared here. Pi squared here. It's a pi squared here. Thank you for pointing that out. So there's a pi squared here. It's a pi squared here. So if I do this, then if I go back and look at my E again, my A is h bar k naught squared E. My delta E is equal to that. And E over delta E is equal to delta k naught over k naught. So you plug this in, this is my delta N. My delta N is equal to V k naught squared pi squared delta k naught, which is consistent with this number over here. Yeah, I think these two numbers are consistent. Okay, this number was obtained using a different argument. This number was just obtained by rigorous summation and converting the summation into an integral, and then I get this to be my thing. Okay. So I'll give you some homework where you have to convert summations into integration and prove some integral identities in the take-home exam. So you better learn this. How to convert the summation into an integral and find a closed form expression for those integrals. Okay, is that fair?
How many problems are there?
I have thought up of 2 so far. Maybe I can come up with the third one this afternoon. Okay. So these are just a lot of mathematical tricks that become useful. Any questions so far? How to convert the counting of modes in a discrete way into a continuum integration? Okay. No questions, and you can do something else then. Let me see what was next on my topic here. I think we talked about photonic crystals, we talked about density of states. The next thing I'd like to talk about is actually surface plasmons. Surface plasmons. I think it's a rather hot topic in nano optics. Let's talk about what that is. Okay, surface plasma. So I'm going to follow some lecture notes which I will send to you from Milwaukee and Hack. They wrote a book on principles of nano optics. I think their book is called So what they do in nano optics in the modern world is actually very similar to what they did in electromagnetics some 20 years ago. They are doing nano antennas, they are doing nano waveguides, we are doing nanoparticles, and we are solving Maxwell's equations essentially at optical frequencies. And the reason why nano-optics becomes important, because if you look at blue light, right? Blue light is about 500 nanometers, maybe 400 nanometers. Okay, your blue CD operates around 400 nanometers. That's why the storage is a lot higher. Before that, they operate with a longer wavelength, maybe infrared, which is about maybe 1200 to 1500 nanometers. So when you go to Blu-ray laser discs, you can store a lot more things because the wavelength is smaller. Okay. And now, because of nanofabrication technology, things of 10 nanometer size can be made. You see that they will make little gadgets that are 10 nanometer size, which is extremely small. And then you can see transistors now. Each node of a transistor is about 10 nanometers, maybe 11 nanometers. They're quite small. That's why we can pack so much thing into your cell phone, because of nanotechnology, the fact that we can pack more and more things. Because of this, you can make very tiny gadgets that are sub-optical wavelength. And then the solving of Maxwell's equations becomes very important, because Maxwell's equations turns out to be valid over a vast length scale, which I say is valid over the subatomic length scale to the intergalaxy length scale, and is valid from all the way from almost DC to optical wavelength. Okay, maybe even UV. When you go to X-ray, maybe there's some other new physics you have to consider. But Maxwell's equations is valid over a very broad range of frequencies, and a lot of people are solving Maxwell's equations now in nano-optics. It's like many years ago we were solving Maxwell's equations in its full glory when we did microwave engineering. XYZ component of the electric field is important in microwave engineering. But now they find that in nano-optics, XYZ components of the electric field is also very important. Okay? And that you cannot treat optical light as a scalar wave anymore. In the past, you can treat light as a scalar wave, because you can think of light as in randomly polarized. I hear you solved the problem, am I right?
Yeah.
Okay, you could derive the formula in the paper?
Yeah.
Okay, good. I look forward to seeing the solution.
All right.
Okay. But you shouldn't come late to school.
Yeah.
Okay.
Where's Tim? Oh.
So nanofabrication actually opens up a very interesting area of nano-optics. And people are doing like optical imaging. And Professor Scott Carney, with his ENSOM, near-field scanning optical microscopy, he claims that he can have 10 nanometer resolution with his ENSOM, plus some interferometric techniques, and he was adding interferometric technique. Okay, with ENSOM he claims 10 nanometer resolution, which is extremely small, much smaller than any viruses that we know. Viruses are on the dimension of microns. Your hair is even much larger than that. Okay, so when you can make something really small, it's actually really amazing. And then you have people like interferometric imaging. And let me see. I think his name is Gabby Popescu, which is also a professor in the department. He's doing interferometric imaging to get 2 and 3D images of the surfaces. And we did that in radar many years ago. You probably heard about interferometric synthetic aperture radar. And that provides you with the 3D image of the surface of the Earth. So by using interference of radar signals, you can actually figure out height as well as just 2D images. Okay, and then what else is happening? Well, some of you heard about the antenna array. Using VCSEL, and then you heard about his talk. What was his name? Ken Choquette, right? Ken Choquette. And a lot of the things he does in VCSEL and trying to engineer radiation patterns of VCSEL is very similar to antenna engineering many years ago. Okay, you just have to make sure that things are phased correctly. But it's a lot more difficult to do all this work at optical frequencies because the wavelength is a lot smaller. Wavelength is on the order of 1,000 nanometers. Microwave engineering is on the order of 30 centimeters, 3 centimeters at 10 gigahertz. So wavelength is that big, but these people are working with wavelengths that small. So no small wonder that all these technologies come about a few decades later. But the physics is very similar. Let me see who else is doing something very similar to classical electromagnetics. Tomorrow, I think Steve Popat will give a talk on optical engineering with the biomaterial in eye optics. You can go listen to his talk and see how much of those is actually classical EM, how much of those is actually modern optics and so on. Okay. So let's just look at the field of surface plasmonics, which comes about because of nanofabrication, because we can make things so small that surface plasmon effect becomes very important. Actually, there are more people who does this kind of thing. I just heard, for instance, Ben Wasserman, right? If you look into, inside Illinois, there's an article in there saying that he's doing nano antennas. And those nano antennas, the physics of which is not very different from classical antennas we did many years ago in microwave engineering. Except that he has to work with these nano antennas at a much smaller length scale. They will have to use the fab lab, the nano MNTL lab, to make this antenna. They cannot do it upstairs here, right? You guys work upstairs here, you cannot make nano antennas here. And who else is doing this kind of work? Let me think. Oh, Logan Liu. There was an article in what is that called? The Wire, right? Is that called the ECE, the Wire? Talking about stained glass windows in churches and how people actually use nanoparticles to make paint. And those nanoparticles actually could affect the color of the paint very easily. And he has an article somewhere saying that he's combining science with art or something like that. Okay, and actually it has something to do with very classical electromagnetics, not very modern form of electromagnetics, but very classical form. And once you understand these classical forms of electromagnetics, you understand actually a lot of what goes on in nano optics these days. What else did I hear in the news? Did you hear anything else in the news? Like we talked to Professor Cunningham and he was telling us about thermal resonances and photonic crystals and using those to detect blood cancer at a nanometer length scale on the order of 100 nanometers. Yeah, you want to say something?
I heard that they found the Roman chalice.
Yes.
When you pour wine or some sort of
Right.
liquid, it changes color.
Yes, yeah.
And they think it's because of some sort of
The nanoparticles, yeah, what is talking about is this Roman chalice. You've probably seen this in many places before, okay? And that the glitter in the Roman chalice is so bright is because the gold It's actually nanoparticle. Gold by itself does not glitter as much. Okay, but when you make gold into small particles, they glitter more. You have this very fantastic brilliance of color from gold. And you will learn a little while, hopefully within this lecture or the next lecture, as to why gold glitters so much when you convert them into particles. Gold by itself does not glitter as much. Okay? So we have a famous saying that's saying that all that glitters is not gold. Have you heard that? About that? All that glitter is not gold. So it's actually gold nanoparticle. Okay, not gold. Gold nanoparticle. We learned that a little while. Okay. So let's first just learn about surface plasmonics, which is an interesting area. We held high hope for a while, but I think it's not going to be very easy to engineer things with surface plasmonics. But you can understand the physics of surface plasmonics purely from classical physics alone. You don't have to actually invoke any quantum physics. And I'm going to follow Nowotny's notation that he uses in his textbook, that a dipole moment is defined to be mu, which is the charge of the electron times the displacement of the electron from its neutral position. And then the dipole moment is given to be dipole moment or polarization density is number of particles times u. Okay, this is the polarization density. It's the particle density or charge density times the dipole moment per particle. And P is called the polarization density. It's usually the number of dipoles per unit volume. And then we often write P in macroscopic electromagnetic theory as just that. We just usually write this as that, and then our displacement flux D is the vacuum displacement flux plus any molecular contribution. This hopefully is coming from some kind of molecules, and that is how we write that. And then we often write this as a effective epsilon, which could be a function of frequency times the electric field. Okay? And that this effective epsilon is equal to a relative epsilon. I'm using notation of Nowotny and Heck. And this is just 1 plus pi. Okay? Pi is usually called a susceptibility or something like that. It has a name too. Okay. So let's talk about the simple theory for dielectric constant, which is actually a classical theory, nothing very fancy. You can call it root sum of your theory for dielectric. And in this theory, you just write down the classical equation of motion, assuming that an electron has an effective mass, and that mass times acceleration gives you force. This is Newton's law, mass times acceleration equals force. And then it will be equal to some kind of an applied field. The applied field is time harmonic, so it has time dependence on this form. It's going to drive the electric charge moving around with that effective mass. Okay, there's a concept of an effective mass in an electron that we will not belabor at this point. But then there's often also the loss term. Okay, this is friction, collision. Okay. That second term is due to collision, and this term is just due to inertia. Newton's law. Okay, mass times acceleration is equal to force. And gamma is some kind of a collision frequency, which is 1 over tau. Okay, is the rate at which the electron collides with the lattice that slows it down. And you can think of this as ME partial R partial T. This is like momentum. And if this is a collision frequency, this momentum times 1 over tau, gives you the rate of the loss of momentum. Rate of loss of momentum is a kind of a force. So this is like kind of an average ohmic force due to collision frequency. Okay, and this gamma is usually given to be some kind of a velocity times the in-free part. This is usually called in-free part. And this is the Fermi velocity. Fermi velocity is the velocity at which the electron will move about, okay, on the highest level of the Fermi energy level, or the Fermi direct distribution. And the highest level is called the Fermi energy. And electrons at that highest level has the highest velocity, and this is usually given to be roughly that thing over there. So you can solve this equation. If you solve this equation, you will get omega squared for the first term. The second term will give you I omega ME gamma, and then will be equal to